Okay, a very good evening, everybody, and welcome to our second show of the English line of videos that we are doing for the DOTliveplanetarium, and to show you some astronomy, to show you some interesting things, and in this show we'll talk to you about the Sun. So, the Sun is a pretty magnificent object, and we're going to tell you a lot about it, but first let me introduce what we normally do and who we are. So, as you can see around us, this is normally the DOTliveplanetarium, and we used to give the shows here, where we have a sort of huge cupola with different cameras that make up the image. We can fly through the universe, but due to a pandemic, we can't anymore, so we're currently doing these shows like this, from home, just streaming. Trying to get Casper on the camera. But yeah, so we do these shows like this now. So my name is Alex, and this is Casper.
Yeah, and we're both astronomy students from Groningen. So yeah, Alex already mentioned it. We're going to talk about the Sun, and we'll do this show again with the same software as we did last time. We're going to use OpenSpace. It's open source software which you can also download at home for free. We already booted it up, so let's move to that scene. As soon as you boot up OpenSpace, this is the view you see. Yeah, we've talked briefly about how this all works during our last English video. So yeah, if you're interested in that, where you can download it, please check that one out. Yeah, we're not going to go too much into depth on the Earth today, but it is where we start off. It is where we are all located at the moment. But we'll first just fly away a bit.
Yeah, and so we can see the orbit of Earth, again the blue line, and the orbit of the ISS, the orange one, and we will slowly move towards the moment where you can see the Moon. And that's this one, but we want to go out further because we want to show you, something else. And for a first moment, we can tell you a bit about how distances work in astronomy. And normally we use kilometers or meters, and what we do right now is we use light seconds. So the distance light travels in a certain amount of time. So a light second, which would be from the Earth to the Moon, that is 1 light second, so it takes light 1 second to go from the Moon to the Earth, and this is a bit how we do that with distances.
Yeah. So here at the top left of the screen, not sure whether you'll be able to see it on a small smartphone screen, but it says our distance to the Earth is now currently about 1.8 AU. AU is a term in astronomy is used quite often. It's the astronomical unit. 1 astronomical unit, so 1 AU, is the distance between the Sun and the Earth on average. Yep. So yeah, right now we've zoomed out quite a bit. So the Earth is right there together with the Moon, but at this distance you won't be able to see them apart from each other anymore. We got the Sun at the center of our solar system. So the solar system is our Sun with the planets around it, also the asteroids and the comets and everything that is basically gravitationally attached to the Sun. So closer to the Sun we see Venus and we see Mercury. A bit further we see Mars over there, and all the way out there is Jupiter.
Yeah, so there's a huge gap between the Earth-like planets, so the terrestrial planets, and the gas giants, and that is usually determined by how the solar system formed, and usually gas is lighter, so it goes further out, and that is one of the reasons why gas giants are much more common in the far shells of the planetary disk. But what is visible very clearly if we wait a while and we move slowly to the right is that they are all in one line.
So we'll now try to look at the solar system a bit from the side, and as Alex mentioned, these planets sort of lie in the same plane, and That might seem pretty odd at first. So here we can see it almost exactly in one plane. But it's a direct consequence of how this entire solar system formed about 4.5 billion years ago. So originally, this was quite a big gas cloud, and due to the force of gravity, it collapsed in on itself. And at the center, it was very dense, and a star formed, which is our sun. And around it, the planets formed, the rocky planets closer by. So that's Mars, Earth, Venus, and Mercury. And then further out, the gas giants, which are Jupiter, Saturn, Uranus, and Neptune.
And out there you can actually see a little green speck, which is, if I'm correct, Pluto.
Yeah.
But it also orbits in a different plane.
Yeah. And that basically gets us to the main difference between planets and stars. So our own sun is remarkably similar to some of these gas giant planets, but our own sun, it produces energy by nuclear fusion. So it emits light, whereas planets do not. So planets do not emit light, they only reflect light. If you go out tonight and you look somewhat towards the south, you'll also be able to see some of these planets. So you'll be able to see Jupiter and Saturn, but they're nicely in one line, so you'll be able to see them in the night sky. The brighter one is Jupiter, it's bigger, it's also closer by, and the other one is Saturn. If you want to know the exact positions, you can find it very easily online.
Yeah. So for now we're going to focus on our sun, and we already explained a bit about how our sun was born. So now let's talk a bit about how the sun actually, what other places where stars are born. So our sun started in a huge cloud of gas, and it was not alone. There are multiple stars being born in the same sort of cradle of gas that has certain clumps that become stars, and we can see one in the next picture. This is the Orion Nebula, if I'm correct, and it is a star-forming nebula. So there's actively stars being created in this nebula, and yeah, it's very interesting to see.
Yeah, so we can see this in the night sky as well, but from the northern hemisphere where we are, we can basically only see it during winter time. So unfortunately, not now. But yeah. Over millions of years, stars form in these regions. The gas cloud in which our own sun originally formed has already been completely transformed into stars, so you can't see any gas cloud around us at night, but we can see other places in which the stars form. And in our whole Milky Way, there are many of these gas clouds, and about one star will form there per year. So let's take a closer look at our own sun. This is a diagram which is made to show all of the different layers that are present within the sun. So at the center part we see the inner core, and this is basically where all the nuclear fusion happens. So the density is very high at the center, which causes very high temperatures, millions of degrees. And that fuses together the elements that can be found within the star, within our own sun as well. So our own sun is mostly made up of hydrogen, and this hydrogen is pressed together, and what occasionally happens is that this hydrogen melts together to form helium, and in that reaction a lot of energy is produced, and this process is called nuclear fusion. It's basically nuclear power, but yeah.
So nuclear power, how we currently are using it on Earth, is we're splitting atoms. So we're taking very large atoms and we're splitting them together. But nuclear fusion, the opposite of fission that I just mentioned, is punching them together. And we're actually trying to make similar sort of energy sources here on Earth. But it's really hard because the sun is so hot and it is so dense that it's really hard to recreate in a lab or in any place on Earth. So because it's like if we look at the gas giants, they also have a lot of hydrogen and they have a lot of stuff that they can do, but they are also not massive enough to actually produce produce these kinds of reactions on a large enough scale to actually become a star. So we're currently trying to do that, but it's still really hard. But we're getting closer and closer.
Yeah, so I think last week they started with a new project. Well, the project was already devised some time ago, but they started building ITER, which is going to be the largest nuclear fusion reactor ever built on Earth, and it's a big step forward in trying to make this work as an energy source. So yeah, let's get back to this picture of the sun. At the center, the nuclear fusion happens, and as soon as the energy is created there in the form of light particles, they travel outwards towards the outer shells. It takes a couple of years actually to travel from the inner core all the way out to the outer layers, because the density is very high, so light particles don't move very quickly through it. They bounce off all of the other atoms that are in there, and as soon as they get to the outer layers, then this energy is basically emitted as heat, which we experience here on Earth as well, especially later this week, because then temperatures will rise to close to 40 degrees. It's all thanks to this nuclear fusion that happens in this star, and it has basically been the energy source of all life that has ever existed on Earth. So we, for example, drive a lot of our cars burning fossil fuels, which are actually remains of life millions of years ago.
Yeah. So when we look at the surface of the sun. Oh wait, no. Let's first go to how. A bit about the surface of the sun. We can go to show you a video about how the sun sort of evolves, and this is a time lapse that used to be in about 10 years of solar data, and we see here a few dates, so we can watch it rotate and how it changes. And you see a lot of different features on the sun. So you see sort of the outer part. If you leave the radius of the sun, you see a sort of haze that's called the corona, which has nothing to do with the virus, but it is just sort of the atmosphere of the sun, of the particles that are in there that light up and that follow certain trajectories almost. You can see them when they are coming towards us a bit, and also when they go past us, you see circles around the surface of the sun, and those are magnetic lines. It's magnetic energy that builds up inside the sun and gets released, and then the charged particles, like the hydrogen and everything else that gets that is very attracted to magnetic fields, follows these lines, and it creates these very interesting sort of pathways that go from one part of the sun to the other.
So yeah, we always experience the sun as some very hot object, but not very active. But yeah, this video proves otherwise. The sun is actually an environment in which a lot of things happen over time. And actually, the sun itself has a cycle of about 11 years in which there's more activity and then there's less activity. Currently, we're basically in some sort of minimum of activity, and we're gradually getting out of this. So in about 5 years of time, the sun will be a lot more active than it is at this time.
Yeah, and we can actually see that on Earth as a result of what is happening. Because of the higher energy levels of the sun, there are more particles of energy that sort of come out and towards the planets, and when they reach the Earth, we see that as the northern lights. So you can, if you want to go to Scandinavia, you can actually watch them, and they're usually way more active during the active period of the sun. So if you want to go, save your holiday to somewhere in Sweden or to a few years, because there might be more solar activity, and so bigger and more dominant northern lights.
So yeah, let's get back to these pictures. So we'd like to show you some pictures that have been taken by a professor from the university. His name is Michael Wilkinson, And as a hobby, he likes to take pictures of the sun, but also other astronomical objects. We do want to emphasize, if you want to look at the sun through a telescope, never do it without special filters. Never point your telescope directly at the sun.
Or your eyes, for that matter.
Yeah, or any binoculars, don't do that. You need special equipment for that. But if you have this special equipment, this is something that you could see. So this is an image that's taken with a special filter for hydrogen alpha. And hydrogen alpha is a very specific color of light that is emitted by hydrogen. As I mentioned before, hydrogen is the main component of the sun because the sun melts the hydrogen together to form helium. And as soon as this hydrogen emits this very specific wavelength, we observe it, then we see all of these textures on the surface, which are all tiny magnetic field lines. So the hydrogen travels along these magnetic fields, and then we also see some of these solar flares at the top of the image, which is hot gas that is being spewed out by the sun. It's caused by magnetic energy that's being built up underneath the surface of the sun, and as soon as it builds up, well, at a certain point it's got to come out, and then it spews out all of the hydrogen gas or hydrogen plasma.
Yeah. So in the middle part, we call that the convection layer of the sun. It is a sort of in-between layer where there are kind of bubbles from the core that come up towards the outer parts of the sun, and a lot of energy is in these kinds of sort of bubbles that move up through the convection layer, and those can sometimes reach the surface, and then this is also very dominant.
Yeah, and you can compare it to, for example, a water cooker. As soon as it gets close to the boiling point, and you see all of these bubbles moving up, and it's basically the same thing as what happens at the sun, but at a much higher temperature. So you get these inner parts that are coming up towards the surface and then cooling down a bit and then moving downwards.
And it is the same for the core of the Earth and the lava that is inside the Earth that is slowly moving towards the crust. There's a lot of convection.
Yeah, very dominant process in physics. So this is another image, and this has been tweaked a bit. So in this image, Michael put in a picture of the Earth. This is of course not a real picture as it was taken from Earth, but this is the apparent, the size of the Earth if we were to compare it to the Sun. So the Earth is a lot smaller. It would fit in the Sun at least 1 million times. So if you already thought that the Earth was a big thing in space, it really is not.
And our Sun is relatively small for some stars in the universe.
Yeah, as we'll get back to in a sec. Some other images. So again, hydrogen alpha for the full sun that you see on the left hand side, but on the top we can see 3 different images of the same region on the solar surface. So this is actually a sunspot, which is a place where gas is emitted from the surface, so energy is released from that place, and then it actually cools down somewhat near that sunspot. So the surface is cooler there. Still, it's thousands of degrees, but it's cooler than the surface around it. That's why it appears somewhat black. Actually, this one has some sort of a heart shape. On the left, we see the hydrogen alpha image. Then in the middle, we see calcium. And then on the right-hand side, we see visible light, which is the same, basically all of the colors that we can see with our own eyes as well. And within these 3 different colors, basically, we see very different features. And that's because we're looking at different layers of the sun. So the hydrogen alpha is basically the outer surface, and then as soon as we move to the right, we look deeper into the sun. And this is a trick that we use a lot in astronomy. We look at all kinds of different colors, all kinds of different wavelengths, to be able to see different things in the same objects. And
yeah, it's a very special process because the color of light depends on its wavelength, and that is also relative to how much it moves up and down in one sort of second. And this is a very interesting process because depending on the wavelength of light, it scatters or it hits or it doesn't hit a very specific object. So if you look at something through different different frequencies of light or different wavelengths, then sometimes some light passes through and some gets blocked. So you can actually watch different depths, or you can watch through objects just by looking at wavelengths that travel through them. This is also why radio waves are used very commonly, because they don't interact with a lot of objects.
So let's move back to open space for now. So here we see our solar system again with the sun in the middle, and this has been in existence for about 4.5 billion years. So the sun has been burning for 4.5 billion years, quite a long time, and it will continue to do so for probably at least 4 to 5 billion more years.
So we're halfway.
Yeah, so yeah, we're sort of halfway. And that is because the sun is very large, so it has a lot of heat of hydrogen, and it will continue to burn it for a long time. And then after that, actually we'll start to burn this helium that has been produced from the hydrogen, and it melts the helium together. But after about 5 billion years, then something special happens within this sun, because currently it forms a very delicate balance between the gravity trying to pull it inwards and the radiation pressure that is pushing it outwards. And right now they're in balance, so it forms some very nice round object, which is relatively stable. But at a certain point, this radiation pressure and this gravitational force aren't in balance anymore, and what happens then is this star will begin to shed its outer layers. So then what actually forms is what we call planetary nebula. Has nothing to do with planets actually, but it's the remains of an old sun, old star. And what remains in the center is a white dwarf, which is basically the core of this past sun, and then around it is a very colorful, generally cloud of the outer layers of the sun. So it's not going to be a big explosion, luckily, for our sun. Though if it's going to happen, then we're still not going to be safe here on Earth. Actually, before all of this happens, the sun already
swallowed.
Yeah, it's going to swallow some of the inner planets because it's going to grow over time. But yeah, we see these planetary nebula all over the place because there are many more stars, all in various different life cycles. So what we can show here in open space is actually where we find those planetary nebulae. So here we can see it, planetary nebulae, and this is all of the places where they can be found.
So yeah, you see a lot of them in the Milky Way, so the broad band you're looking at around the middle of the screen, and that's where the most are found, because this is the place where stars are most common. They appear the most because, well, the galaxy, our Milky Way is a disk, and there are a lot of stars in there, so it's really easy to find other stars there instead of above and below. But you can still find them, but that's why mainly they are concentrated over there.
Yeah. And planetary nebulae are often very colorful because they have all of these different substances in there which have been formed in their host star in the past. And they also continue to glow for quite some time after they ended. So yeah, very popular also to observe among amateur astronomers. If you happen to be able to use a telescope or go to an observing night anytime soon, very big chance that some of these of these telescopes will be pointed at planetary nebula.
Yeah, it's also very easy to, if you don't go to a observatory in the near future, you can also look for them on the internet, because there are a lot of beautiful pictures of planetary nebula, and you can just Google different kinds of planetary nebula. But we can show you.
Yeah, well, we're going to show you something more spectacular, I think.
Something more spectacular. We're saving something more spectacular, but you can Google them.
Yeah. Because well, we're going to show you something else, because, well, I guess what all of we would have hoped is that the sun would have exploded in about 5 billion years. But to be able to explode as a star at the end of your life cycle, you're going to need to be a bit bigger than the sun. So the sun is a very average star. But if we look out there into space, we see much bigger stars quite frequently. And one of these stars, which has been in the news as well quite recently, is Beetlejuice. And over here we can see a picture of Beetlejuice. So it's the orange blob that can be seen in the back. And Beetlejuice is one of the very few stars that can be observed as an actual object and not like a point source. So most of the stars that we see in the night are simply point sources. So they're a single pixel, even if you look at them with the largest telescopes on Earth. For Beetlejuice is different, because Beetlejuice is so large that we can observe it as a blob. And if we put over the orbit lines of the planets of our own solar system, including the sun, this picture that you see here is what it would look like. So if our own sun would be replaced by Beetlejuice, then it would basically swallow all of the planets up until Jupiter, and then Saturn would be orbiting very close over the surface of the star. So it's a huge star, and you can see it in the night sky, but again only during winter time, because it's very close to the Orion Nebula that we saw before. And Beetlejuice is very special because it is basically on the brink of I would say extinction, but it's nearing its death as a star, because it has burned up most of its helium by now, and within the very core, very heavy elements are beginning to form. And as soon as this star will begin to form iron in its core, very specifically iron, then it will last only a couple more seconds, and then the whole star is going to implode on itself, because there's no radiation pressure anymore coming from the center. And then after that it will explode violently in what we call a supernova. And well, Beetlejuice will do so in about maybe a year, maybe 100,000 years, but very soon, for astronomical terms. But we see other remnants of supernovas all around us, and one of these supernova remnants is the Orion Nebula. This is an actual image that's been taken with the Hubble Space Telescope. And we see all of these different colors within the nebula, and they are emitted by all the different elements that can be found in there.
And it's actually pretty funny, because this happens more often than that small stars explode, because if you have a star that would be 10 times bigger than Earth, its lifetime would be only 1,000th of Earth. And if it gets even bigger, well, for every 10 times it gets bigger, you can add 3 zeros, and that's how smaller or how longer the sun's life would be. So yeah, so they happen pretty often, and they're very gorgeous. So we can show you where you would be able to find them in open space, because just like we could show the places where planetary nebulas are, we can also show you where supernovas are. So we're going to go back to open space.
Yeah. So right now we're still showing the planetary nebulae, but we can also show you the supernova remnants. They can be found also in the plane of the Milky Way. So these are supernova remnants that we can actually observe as some sort of cloud. And a supernova in our own galaxy happens every couple of 100 years, but supernovas also happen in other galaxies which are way further out. And we won't be able to see their remnants, but these explosions, the moment a supernova happens, these explosions are so incredibly bright that we can see them basically at a distance of millions and millions of light years. So we can see them in other galaxies way further out. Let's get back to these pictures that we had here. So this was the Orion Nebula. But yeah, we're all wondering what remains at the center of these supernovas, because the gas is blown out, but it also imploded, and the moment it imploded, it could form a black hole. It could also form a neutron star, but occasionally it's a black hole.
If it's large enough. And the interesting about a black hole is that light cannot escape it. And this is what you're looking at now. It's not a picture of a real black hole. There was one in the news, I think, a year ago, something like that, maybe a bit less. And there was a picture of it, but it's really hard taking pictures of it. But that was the first one. And here's a sort of simulation how it would look if you would be this close to a black hole. And it's not advised to be this close to a black hole. But what happens with a black hole is that it's so massive that it attracts a lot of things towards it. And it's really hard for gas, light, or anything else to escape. So the planet you are looking at is having a really bad time. And something that's important to note is that the border that you're looking at is not the moment you are in the black hole. This is the event horizon, because the black hole is a lot smaller. The border that you are seeing over here, oh no, we can't point at that, that's pretty funny. But the border you're looking
just
at,
over your head.
Yeah, just over my head here, that is the event horizon. And that is the point where nothing can escape anymore. So even light gets sucked in, and that is why you're not seeing light further into the black hole. And the gas is heated up because it's rotating around it and it's getting swirled like our planets do, but a lot faster, around the sun, but a lot faster. So they heat up and they create a lot of light, and how the light is disturbed is pretty much what they're trying to show you with this picture.
So this frame was actually used for the movie Interstellar, which is of course a Hollywood movie, but the actual modeling of the black hole was done by some very famous astronomers. So it is rather accurate. So yeah, with that we basically closed the loop. So we started off with the sun being formed in a protoplanetary disk within some of these star-forming clouds, and then all the way in the end it ends up as, in case of our sun, a planetary nebula, or a bigger star, supernova with supernova remnants. And of these clouds that are being formed by supernovae or planetary nebulae, new stars can actually form, because we again have gas clouds. And these gas clouds can accumulate over time, due to gravity, new stars can form, and that's when you get to next generation stars. So astronomers very often talk about first generation, second generation, third generation. It is basically how many times a star has been recycled. Yeah, with that we basically closed the loop for now. I see we're we've also passed half an hour by now.
Yeah, so if you have any questions, you can still ask us right now. We'll be here for about 5 more minutes. So if you have any questions, then please feel free to ask them. And also subscribe to the channel if you want to see more of these kinds of movies. And if you have any interesting places you want to go for following shows, you can also ask us, or yeah. And we can try to make a show about something else next if you're interested.
Yeah, so you can use the YouTube chat box to ask your questions. Yeah, and we hope to definitely see you another time. And we'll keep you updated on when we'll be doing shows in DOT again. Okay. Don't think there are that many questions anymore. So
See you next time.
See you next time.
Goodbye.
Bye.